Hi everybody, today we're going to have a look at curve sketching. Curve sketching is quite an important part of calculus, and we're going to have a look at how that works for a function and its derivative. So for a function y, it has, for a polynomial, it'll be in the form a n x to the n plus a n take 1 x to the n take 1 all the way down to a0. And the order of this polynomial is, we say, is order n, the highest power of the unknown x. Now when we take the first derivative, the order of the first derivative will be n take 1. So this is important because if you have a quadratic function to start with, your first derivative will be linear. If you have a cubic function to start with, your derivative will be quadratic. If you have a quartic to start with, the derivative will be a cubic, so on and so forth. And so if you know the order of the original function, you also know the order of the derivative and what it will look like. So here's an example. So if y equals f of x and it's a positive cubic, then the derivative will be a quadratic. It will have 0, 1 or 2 solutions. The point of inflection of the cubic will be at the stationary point of the derivative. So if we have y equals x cubed plus 3x squared, this green line, y prime will be 3x squared plus 6x, the quadratic here. I've drawn them both on the same set of axes. The inflection point will indicate the saddle point on the original function. So the turning point on the derivative indicates the point of inflection on the original function. Where the gradient is 0 will be indicated by 0 on the derivative graph, which tells us where the stationary points are. That's indicated here. The derivative 0, stationary point. The derivative 0, also stationary point. Now this is probably harder to understand than the saddle point above. Now this would also indicate to us a horizontal point of inflection if one existed. Now, once we've determined where the stationary points are, we have to figure out whether they're a maximum or a minimum. Now we can do this by understanding the geometry of a cubic, or we could just substitute the values of x back into the original function and looking at the values. The one that's bigger, that's going to be the local maximum. The one that's smaller, that'll be the local minimum. So we'll use that technique here. We know that if we're doing this algebraically and we didn't have the graph sitting next to us, we would take x equals 0 and substitute that back into the original equation. And we'd get 0 plus 3 times 0 equals 0. So y0 is 0. We don't know if that's the maximum or minimum, we just know it's a value at this point in time. Then we substitute in negative 2. Negative 2 equals negative 2 cubed plus 3 times negative 2 squared, which is 4. 4 is obviously bigger than 0. 4, negative 2, 4 would be the maximum, and 0, 0 would be the minimum, as we can see on our graph. We can also look at the global minimums and global maximums by looking at the extrema. So at negative infinity, if we substitute negative infinity into the highest order term, which would be x cubed in this case, positive infinity cubed will still be positive. So as x tends to positive infinity, it's going off to infinity. Negative infinity cubed will be negative infinity. Negative times negative is still negative, and thus we can see it's going off to negative infinity down here. Thus we can get these two values. So as x tends to negative infinity, the limit of x cubed as x tends to negative infinity is negative infinity. As x tends to positive infinity, it's off to positive infinity. Now, what am I trying to say here? The roots of derivatives indicate stationary points of the original function. This is obvious as when the derivative is 0, it indicates points on the original curve where the gradient is 0. So where the derivative is 0, here and here, it indicates where the gradient is 0 on the original function. Or the rate of change is 0, or the instantaneous rate of change is 0. And there are potentially 3 stationary points looking at where the gradient is 0. It's where there's a maxima, or a minima, or a horizontal point of inflection. i.e. where the tangent's horizontal. So let's have a look at the function again and see if we can make sure we determine everything. So the other thing that we can see from the derivative is when the function's going to have a positive slope and when it's going to have a negative slope, when the values are increasing, when the values are decreasing, and when the values are increasing again. So when the values are increasing, the derivative will be above 0. When the values are decreasing, the gradient will be negative, it'll be below the x-axis, and when the function's increasing again, it'll be above the axis. So you can see here, increasing, above the x-axis. Decreasing, the slope is negative, below the x-axis. Increasing, above the x-axis. And this is counterintuitive. Until somebody's shown it to you, it's not really that obvious. And when it's 0, the gradient is 0, it's a stationary point. Now, we'll deal with the inflection point a lot next year, but I'll just point out here that where the first derivative is 0, you can find the inflection point. You can find out when it's 0 by differentiating the derivative and looking at where the slope of the derivative is 0, so treating this as the original function. But we don't have to deal with second derivatives this year. And we make that point here. So what we can do now is we can sketch the derivative based on information that we've got from the original function. We could do that just by taking the derivative and substituting some points into it. And if I have a look here, I'll just bring everything back on the page. So over here, I substitute a few points in f of 1, f of 2 into the derivative function and plot them. And it shows us some interesting things. So if I have a quadratic, if I take the derivative of it, I get a linear function. It goes from x2 down to x1. So here's my original function, and lo and behold, my derivative is linear for x squared. The derivative becomes 2x. Now, what does that look like? Well, the slope over here is fairly steep. It becomes less steep until it gets to 0, then gets more steep, and we can see that the gradient is slowly increasing from a highly negative value up here to 0, and then to a positive value. And that's what's shown by our graph. At negative 1, I'm sorry, I've gone too far off this graph. Negative 1 here, the slope is negative 2, which looks about right. Then when we get to 0, the slope is 0. When we get to 1, the slope is 2, which sounds right just by looking at them. And then when we get to 2, our slope is 4. It's significantly more than it was here. And if we plot those points, we get a nice line. There we go, we've sketched it. Now here, let's try and go backwards. It's hard to go backwards without more calculus. We'll learn integration later, and that focuses on going from a derivative back to the original function. And one of the difficulties is we lose a bit of information when we take the derivative. When we take the derivative, where's a case? Here, say. Oh, here. If there was a constant on here, we would lose the constant. And that constant tells us how far the function shifted up or down. Wasn't a particularly good example because it didn't have a constant, but neither does this one. But here we go. So we have a derivative. That's what it looks like there. and we're trying to get the shape of the original function. We can't tell where it is on the axes because we don't have the vertical shift. But we can get a general idea of what it's going to look like. So we know that the gradient's going to be 0 where it crosses the axes. We know that it's going to have an inflection point where it has a stationary point. And we know that the slope is going to be positive, less than here, and the slope is going to be positive on this side, and the slope is going to be negative for this region. So now we've gotten all our information that we can possibly get from our derivative, we can start to plot the points. So what I tend to do is for the stationary points, I'll just draw a dotted line. I don't know where at this point on the dotted line it exists. I'll put the inflection point in. So there's a point there. I'll look at where the graph has to be positive. So the graph will have to be positive on this side, and the slope will have to be negative on this side. And typically you would do that. Let's do it. I think it might be better in this case to actually just do what needs to be done. I'm going to get rid of the line for the moment. So I'll plot those points on, and I'll say, all right, well, it needs to go in that direction, and it needs to go in that direction. I've got a square function here, and it's a positive quadratic, so I'm going to end up with a positive cubic. So I'm going to need that sort of shape. So now that I know that, I will draw in a shape through my points. That wasn't very good, so I might try again. Starts here, goes up to there, goes through there, goes through there, and goes up to there. And now I've got a possible shape. The values aren't going to be correct because I don't have enough information to do that at this point in time, but it's not too bad. And there we go. That's a bit of curve sketching, and we'll keep refining our technique over time as we learn more and more calculus. Thank you, everyone.